So these are all rare events that are hard to handle. Nevertheless, people expect that an autonomous vehicle handles this correctly because it's a life or death situation. And from a statistical point of view, you need to test drive an autonomous system, like in this case, an autonomous road vehicle, for 440 million kilometers to demonstrate that you're as good as a human with 95% confidence. Let's say if you want to be 10 times better, which is probably required, otherwise the technology wouldn't be accepted, then you need even much more test kilometers. And even that number would amount to 12.5 years of testing with 100 vehicles operated around the clock. A slightly different view compared to the statistical view would be to look at the test coverage. So for instance, if you have a very simple test case, where you just have one autonomous vehicle following a single lane, then you want to test whether it follows this lane depending on the width of the lane, the curvature of the lane, or maybe the change of the curvature over the length. Then you already have 3 parameters, and for each parameter, maybe you want to test 20 values, and then you already have 20 to the power of 3 values if you test all combinations. But then you have not maybe only one lane, but several lanes, maybe 5. Of course, the number is debatable, but it's just an example. Then you already have 20 to the power of 3 to the power of 5 just for the road topology. And then you have a lot of further test cases because you have other traffic participants with different X, Y position, orientation, and velocity. And of course, there's not only one other traffic participant on the road, but several others. So you have, again, 20 to the power of 4 to the power of 10, plus all the different cases when of all the different parameters of the ego vehicle. And in this case, we assume 8 vehicle parameters. So then you have more than 10 to the power of 80 scenarios, which are impossible to test upfront. Some people argue, of course, that you don't have to test all combinations, but you can never be sure that the system works then under all combinations. And even if you have that many combinations in between these combinations, there's still areas that you haven't tested, which could potentially lead to an accident. So the idea we follow in my research group, though, is then that we don't want to test the safety before the vehicle is deployed or the autonomous system is deployed. As you will see, this also works for any kind of autonomous system. We want to verify the safety during its operation in an online fashion where we consider the current situation, consider the possible actions, do the verification before we perform this action. Only if this has been verified to be safe for all times, then this action is actually performed. So we can consider all kinds of scenarios. So we don't have these holes in the test coverage, and we only have a much smaller verification problem. We just have to verify that the system is safe for the next seconds, plus that the fail-safe maneuver that I will introduce in a minute has to be safe. So we have a much simpler verification problem. However, we then need an efficient and online adaptable verification procedure, which I will present in this talk today. And the impact will be to reduce costs. I mean, if you have a safety critical system, at least 50% of the development costs are verification costs. And you can imagine that building an autonomous system costs billions of dollars. And of course, you will have fewer liability claims, which is good as well, not only for the reputation of the company, but also in general for the greater good of humanity, that nothing bad happens, and you can enable safe autonomy for a wider range of operating conditions. So I will introduce now the basic concept, and after that I will maybe have the first round of questions, because that is something that everybody should understand, this underlying principle of this talk. So one principle is that we don't look at single executions of systems, but we look at sets of possible executions. So for the ego vehicle and other objects around the ego vehicle or ego system, we compute all possible solutions that are bounded by sets. And if these sets do not intersect, we for sure can verify that there will be no collision. But we can also use the set-based methods to, for instance, verify more complicated specifications, such as traffic rules that you cannot drive over red lights, that you have to respect, that you have to yield other traffic participants, or that you have to keep a safe distance. And how the question now is, how do we combine this with some motion planning module? So this motion planner can be an AI system, it can be a classical optimization system, doesn't matter. It produces this blue trajectory, and before we compute this optimal trajectory, we often assume a certain behavior of other traffic participants. In this case, we assume the other vehicle stays on its lane and keeps its velocity. However, in contrast to other approaches, we also compute the reachable set of other traffic participants, which includes all possible behaviors. And we compute this failsafe trajectory B, which brings the system into a state where it can stay indefinitely without causing any accident. And yeah, so then in the next step, the other traffic participant does something unexpected, but we know, because it can only produce behaviors within the reachable set, that the previous failsafe maneuver is still safe. So we will always be safe. Nevertheless, we try to find a new intended plan A prime with a new failsafe maneuver B prime, and try to verify it before it branches off the failsafe trajectory, so that we don't have to engage it. It could be that we engage the failsafe trajectory, but then we don't have to execute it until the very end, so that we, as soon as possible, continue our movement. One more word regarding the safe state. So the state should be safe in the sense that you can stay in the state for all time. So in a road vehicle, that could be stopping. Of course, if you're on a highway, then stopping is not always safe. Then we are looking for states where we can engage a provably safe adaptive cruise controller. And in other areas, different states could be states where you stay safe for all time. So in the previous project with Sebastian, we had, for instance, these loiter circles as states, or like a limit cycle where you can stay forever without causing any accident. Okay, so this is the basic idea. Are there any questions regarding this concept so far?
I think we can do questions at the end.
Okay, okay, good.
Yep.
Yeah, then I'll just continue.
Thank you.
So one thing that I haven't shown on that slide is we don't assume that we follow planned trajectories perfectly, as shown in this figure, but we also consider here sensor noise, disturbances, and unmodeled dynamics, and of course the trajectory tracking control of the ecosystem, which doesn't perfectly follow a given path or given trajectory. But I didn't want to squeeze it into the other figure. This is something we additionally do. And also, we don't only use this for autonomous driving, we also use this for safe human-robot coexistence. So there will be a video at the end of the talk showing this other application. And we also use it for energy systems to ensure that despite the uncertainty in energy production of renewables, that we meet voltage, frequency, and phase limits in the grid. We are also planning to use formal methods for quantum computing, but that's so fresh, I have no results on that yet. But the approach is applicable to many application areas. This slide is there to because there's always a question, why don't you use probabilistic methods? So I always show now that we also used that in the past. It doesn't mean that probabilistic methods are bad. They just have advantages and disadvantages, and the set-based methods are less researched. So here, this is a slide for my PhD thesis where we computed, or the future collision probabilities of an autonomous vehicle when it follows certain trajectories, given the prediction of other traffic participants like this bicyclist here or this other vehicle. And then you get these probabilities over time when an accident might happen. So that's good for threat assessment and for guiding long-term planning. However, it's very bad for providing accountability. So in an autonomous vehicle, there will be components of different suppliers like perception systems or actuators and so on. And every system has certain issues. And with set-based methods, you can have these contracts and say, okay, the sensor system has to have at least this accuracy, and then maybe the motion planner has to have at least this accuracy and so on. And if you have set-based methods, you can always detect which module didn't provide the promised accuracy. So in stochastic methods, this would be blurred. And the the rarity of fatal accidents is, so fatal accidents are very rare. So you have around 20 deaths per 10 to 9 miles in the US. This translates to a probability of something in the range of 10 to the -9 for a prediction horizon of 0.2 miles, which is kind of the sensor range of a good autonomous vehicle. And even if you accumulate rounding errors, you often have this kind of floating point errors. So it's very, very difficult for probabilistic methods to get the accuracy needed for safety verification. And that's why we want to use set-based methods, because we also want to ensure that the system is provably safe, which would provide the maximum confidence for the passengers of this vehicle. And we believe that this is also viable. And as you can see later on in the videos, we already did some test drives using these set-based techniques. So in order to prove correctness, you need a formal model, you need a formal specification, and a formal verification method. And then you get a provably correct result, which either says, yeah, your action is correct or your action is not correct. So basically, we have these 3 areas: how to obtain a formally correct model, how to obtain formally correct specification, and how do we verify safety given the model and the specification. So regarding the model, this is a little bit tricky. So in computer science, there are things where you can prove that like a model includes all behaviors of a concrete implementation. But in physics, just alone by the Heisenberg uncertainty principle, like I don't know if anybody, one of you had quantum physics, you can never have a perfect model. So what we do is we inject non-determinism into the models so that they produce more than one behavior for a given initial state. And we try to inject as much non-determinism so that we can capture all the real measurements we have from the real system, but not too much, because then the system is so conservative, or the model is so conservative, that we can never verify a certain action. And then once you have this conformance relation, you can prove correctness of the model, and then this safety translates to the real system, because this real system doesn't produce any further behavior that the abstract model wouldn't have produced already. So the classical conformance relation to transfer these safety properties is trace conformance, and as I said, it comes more from the computer science, and it requires that the abstract model produces all behaviors of the real system. But for physical systems, that's really hard, because the slightest deviation would destroy trace conformance. Instead, we came up with something called reachable conformance, where the set of possible behaviors, or the reachable set, so the set of states that you can reach of the abstract model, has to include the reachable set of the real system. And the real system, of course, we cannot compute the reachable set. We can only compute the reachable set of a model. So instead, we will collect a lot of sensor data. And if all the sensor data is included in the reachable set, we say that it's reachable conformant. So there's several methods to obtain reachable conformance. One is we have a nominal model, we have the real system, and then in order to match the model so that the behavior exactly matches that of the real system, we have to inject disturbances and sensor noise, and we use some optimization methods to inject this in an optimal way, and then we collect these injections, and these injections will be then bounded by a convex hull, which will then be the uncertain input to a nominal model, so that the nominal model would produce all behaviors of the real system. So here you see some data from real test drives. So these are the inputs to the vehicle. In this case, we had acceleration and curvature. I mean, curvature could be used, or you can use a steering angle. That's essentially, you can convert one into the other. And then you see here some disturbances that we injected so that the behavior matches up to a certain epsilon bound. So of course, the tighter the epsilon bound, the more accurate, but then the longer the optimization takes. So that's one method, but we have several to have these high confidence models. Now let's talk a little bit about formal specifications. So for instance, for human robot coexistence, we use some isonorms. For smart grids, we use some grid codes, and for autonomous driving, we use traffic rules. So first we have to make them more concrete, because as a human driver, you should maybe have a sufficient safe distance and so on. But for an autonomous vehicle, we can actually compute the distance required to avoid a collision. So we use more precise formulas to decide whether a predicate is true or false. And then we combine these predicates using temporal logics to replicate these traffic rules. And then we translate these temporal logics into a theorem prover that produces provably correct code. Right now, we also produce, like, we only perform for some rules step 1 and 2 and then directly implement it in C++, because 3 and 4 is very labor intensive, and for quick testing, we just use C++ code, which is not provably correct because somebody might have made a mistake during the implementation. But later on, then we would do step 3 and 4 once we see that this rule makes sense. So just an example for concretization. So if you are steering this blue Ego vehicle and you perform a lane change, you might force this green vehicle here to slow down. And the question is, to what extent are you allowed to do that? Because if you force it to do a sudden brake, then this vehicle might not react on time, but then usually the blue vehicle is at fault because the lane change is too aggressive. But to some extent, you can kind of force this green vehicle to slow down. So we need this threshold that we determine together with lawyers. And that's one example how we concretize traffic rules. And as a high-level overview, the kind of traffic rules that we have already formalized are that road users should not damage infrastructure or other road users. You should always drive on the rightmost lane except for overtaking. So on US highways, this is not required, for instance, but on most European highways, speed must be adapted to road and weather conditions, speed limits, and other vehicles, obviously. And then vehicle distances must be such that collisions are avoided. And braking should only be performed for safety reasons. And priority vehicles are exempt from traffic rules. We also have a lot of rules for right-of-way and for intersections and so on, which I've not listed here. This should just give you a kind of quick overview what kind of rules we have already formalized. So now we have the specification, we have the models. Now we have to prove that the model adheres to the specification. And in our research, we use reachability analysis because it can be used for online computation. Other people use things like theorem proving, but usually this requires user input and then it's not usable for online verification. And reachability analysis essentially gives us everything we need. We can verify all the specifications I've already shown to you, given a set of initial states, uncertain inputs, and uncertain parameters. So what is reachability analysis doing? Essentially, if you just simulate a nonlinear differential equation, as shown here, you can choose an initial state and you choose some input, and then you get one solution. And if the solution doesn't hit an unsafe set, then everything is fine. But of course, you can have different input trajectory. You have different disturbances acting on the system, so you don't know exactly which behavior you will, or which disturbance you will get. And you can have different initial states because you cannot infer always the correct state of a system because you cannot measure all states. You have to use observers, and the observers are inaccurate, and you also have sensor noise. So if you would then sample a finite number of trajectories, then you can only falsify and say and show that something is incorrect, but you can never prove correctness. So for correctness, what you have to do is you have to bound all possible solutions, and if this bound, which is then a reachable set, doesn't intersect with an unsafe set, then you can prove correctness. Unfortunately, you cannot compute this exactly, except for very special cases like linear systems with purely imaginary or real eigenvalues. But we can tightly over-approximate these reachable sets, and this over-approximation can be made arbitrarily small, but not to zero. The error cannot be made to zero, but arbitrarily small. So it's more a theoretical obstacle. In practice, this always is sufficient. And if you have a linear differential equation, then like x dot equals ax plus u of t, then computing the reachable set is particularly easy. You just have to compute first the homogeneous solution, where you multiply the exponential matrix with the set of initial states, and then you add the input solution. So this is the convolution integral for those who had systems and signals for fixed input. So we first look at the fixed input and then the deviation of this fixed input in the second step. Now in the third step, in the second step, we compute the convex hull to kind of approximate all solutions in between two time points. And then we enlarge this convex hull to also account for uncertain inputs and also for the fact that the trajectories have some curvature if they go from one point in time to the next, which we didn't, or which we ignored in step 2. And then this repeats over and over again. And so for nonlinear systems, of course, we need some extra steps. And there exist many, many different approaches in our tool Corof to compute these reachable sets, but the simplest one is as follows. We start with the initial set, then we compute the set of the linearized system dynamics for one time step using the approach I've shown on the previous slide. But then, of course, we ignored the fact that we have some linearization errors. So then we simply guess the set of the linearization errors, inflate this reachable set, and then check whether this guess was okay or not. And you can check this, for instance, using interval arithmetic, which is a formal method, which scales very well. So if you're interested, I can tell you more about this later on. And then usually in 1 or 2 steps, this converges. And then you do the same thing for the next time interval and so on. And then you get this reachable tube in which all the solutions have to lie. And this scales fairly well. So for nonlinear systems, this scales to with n to the power of 3, where n is the system dimension. Previous approaches had exponential scalability, so we can also compute systems with 100 or 500 continuous state variables. Okay, so now we can compute these reachable sets. We also checked whether the results are conformant, so whether actual behavior lies within these reachable sets. So one of the earlier tests was that we used this 8,543 vehicles from a data set in the US. Now we have also our own data set with even more vehicles, but this was the first check. And we could see that all the predicted behaviors lie in our reachable set. That, of course, is trivial because you can always make this very conservative, but we also showed that this is not that conservative. So in blue, for instance, you see solutions with a high fidelity simulation model. And in gray, you see the reachable sets. When you follow, let's say here, a lane. So this is a road fork. You can go left or right. This is the option when you go right. And the blue dots have been obtained with rapidly exploring random trees on this high fidelity model. And you see that actual behaviors are very close to the reachable set. So it's not much bigger than what you would see in real traffic. Of course, we also have to talk about computational complexity because you don't only have 1 or 2 other traffic participants, but sometimes tens of other, or even up to 100 traffic participants that are relevant. So what we then do is we don't compute the reachable set of all traffic participants, and we don't compute it until the very end. So one thing we do is that we have several abstractions of our model, and that we compute the reachable set of the first abstraction, second abstraction, third abstraction, then intersect these reachable sets, and then we get the reachable set of a traffic participant. And then we see whether it intersects with the ego vehicle or not. But a simple trick, of course, is that we only compute up to the abstraction that already shows that there is no intersection, and then we don't have to compute further abstractions. That's one trick. And the other trick is that we can reuse reachable sets because reachable sets are always true. Yes, they true for all times. And so if you want to know possible behaviors for the next time step, it suffices to only compute the reachable set of the next time interval. The only thing is if you don't start from scratch and only reuse previous reachable sets, then the reachable set will inflate more than it should because you don't consider the new measurements of the system. However, if right now you need a solution and have not much time, then you can do this trick. And then if you have more time again, you can refresh the computation. So these are some early measurements. Now we have a faster C++ implementation. So sorry, I haven't updated these slides yet. But you see that with this online approach, you would be 8 times faster to verify this situation here in this intersection. So then it only took 12 milliseconds. In MATLAB, in C++, it's even faster. And verifying this situation here, for instance, was 47 times faster, and then only required 3 milliseconds, and so on. So you will also see in the videos that we can compute these reachable sets fairly quickly in real time. We also use reachable sets for motion planning, not only to verify motion plans. For instance, if you want to plan something in collaboration with other agents, and then you have to issue that if each agent has m plans, then you have m to the n power possible combinations. And to avoid this exponential blow up, what we do, we compute the reachable sets and then negotiate the intersections of the reachable sets using some auctioning mechanisms which have polynomial complexity, so that then each agent becomes its own bubble, and then you can plan within each bubble independently. So then you have just n times m possible plans. Good. So all that you've seen is implemented in our tool Cora, which is freely available. So it's a general purpose tool for formally verifying hybrid systems, so mixed discrete continuous systems. And with Cora, we also participate each year in our ARCH competition, which is a competition for formal verification of hybrid systems. Then we have also specialized tools, for instance, for autonomous driving. So Spot is a tool for set-based prediction of other traffic participants, and Common Road is a benchmark suite for motion planning of autonomous driving. But we also have specialized tools for human-robot collaboration. That a tool, for instance, called Zara. And we also have a new tool for benchmarking human-robot coexistence, and that tool is called Cobra. So here you see set-based prediction of surrounding traffic participants recorded from real test drive. So you see here in the bigger here on the left, the reachable set of all times. Otherwise, you had a lot of flickering, and because of that, it seems like it's not safe because the red area intersects the green area. But by the time for instance, the eco vehicle is at the last rectangle of the red area, the green area vehicle is already somewhere else. So this is a little bit, you have to know that if you would plot it for different time steps, there would be no intersection. So here's a situation where you see the whole pipeline. So this is an intersection in Munich, and you see first how we predict other traffic participants using reachable sets. Then you see how we verify the phase of trajectory, and then how we continue with the intended plan. So the black line shows the intended plan, the red line is the phase-if plan, and we verify whether it's safe to start with the intended plan, then execute the phase-if plan, and that's safe. And then in the second part of the video, I will just show you the planning without the verification part. And you will see that it's not very conservative how the vehicle moves. So we let this bicyclist through, but then we take the left turn before this other traffic participant. It's quite tight, but you will see that it was formally correct. So it's intentionally there because people always say, yeah, if you compute with sets, then the vehicle would never be able to move. But we haven't really encountered this problem. Of course, what we do is we don't only consider the physical limits, but also consider traffic rules, so that it's not too conservative, the results that we obtain. This shows how we make use of reachable sets for collaborative driving, where we plan the movement of several vehicles at the same time, because of course it's you have more efficient traffic and safety improvements if you do this collaboratively. So then, here you see the solution after computing the individual reachable sets and negotiating the reachable sets. So the next scene shows a more complicated scene where we want to pass a static obstacle, and then we have oncoming traffic. Again, here we computed the motion plan together with the reachable set to save computation time. And this is a situation at an intersection where we checked if we remove traffic lights, whether we can efficiently negotiate behavior. And then this is a situation with 4 vehicles on the highway. And also that was where we were able to compute this in real time. We also apply our formal methods for safe reinforcement learning. So without our method, during reinforcement learning, you would cause a lot of accidents, as you see here. In a simulation, of course, this is not an issue, but you also want to perform reinforcement learning on real systems so that you don't have the sim to reality gap. And then you can use the safety layer, which is switched on now, to avoid collisions. We have also seen that in simulation, you converge faster to good solutions because the reinforcement learning agent doesn't explore areas of which we already know that they are not safe. We also applied this to mobile robots. Here you see the situation required by the ISO norm. This is a situation where you have 2 pedestrians, the green circles, approaching this robot, which is indicated by this blue circle. And in this light area, if when a pedestrian or human is in this light area, the robot has to slow down. And if it's in the dark area, it has to completely stop. So in this case, the robot has to completely stop. And if you use our online verification, the robot doesn't have to stop because when it slows down, the time until it comes to stop is reduced. And then the prediction horizon for the other traffic participants is reduced. And then the robot essentially slips through and doesn't have to stop while preserving safety. We have also done this in a real test, or we tested this in a situation where vehicles should be shipped from a factory, let's say to a ship or to a train. So this is not really autonomous driving, it's just autonomous driving on factory ground, where the vehicle is basically receiving the sensor information from infrastructure and the commands via cellular network. But there also our safety method has been used. And we also use this for modular robots. So there we don't only consider the safety issue, but we also looked at this interesting problem of creating robots out of fixed modules in a way that the modules program or the assembled program, the assembled robot programs itself. So this was the set of modules we used, and in each module, and then we had information about its kinematics, its dynamics, and geometry. And once you assemble the robot, this information is collected, and then we build like a kinematic model, a dynamic model, and a collision model. And the robot is usable out of the box because of the self-programming capability. So here you see, for instance, gravity compensation. And because we use online verification, no matter how you assemble the robot, it will always be safe. And as you will see next, the principle is exactly as for autonomous vehicles. The only difference is now that the reachable set is computed of the human body instead of other traffic participants. But also here we then have this fail-safe trajectory. So here you see how this runs in real time. So here we verify that the robot never moves before the human touches it. We also have some variants where the force is limited and the robot would not completely stop. So here you see some reachable set of 1 arm, for instance. So this is the situation with the 6 degree of freedom robot. And if you reassemble it to, for instance, an 8 degree of freedom robot, as shown next, then this is also safe out of the box without any reprogramming. So this has also been commercialized. So we have this startup called Robco. I can also show you the website later. Initially, it was called Kia Robotics, but then the vehicle manufacturer Kia, so KIA, said, no, that's not okay. This was an early prototype where we showed these capabilities that you can reassemble the robot. So in this case, we made 2 robots out of 1. This was a 6 degree of freedom robot, but because of the rotational symmetry of these lamps that we moved from one ramp to the other, it was sufficient to use just a 3 degree of freedom robot. Here we still had to use screwdrivers. The new models that can be bought are just, you can just click them on essentially. And yeah, it's usable out of the box. Good. Then I already conclude so that we have enough time for discussion. So I've showed you how to compute all possible behaviors of dynamical systems, where we considered uncertain initial states, disturbances, and parameters. By assuming that all behaviors of the real systems are captured by adding uncertainty, we can prove safety, also for real systems. And the computation of the systems that we already realized is faster than the maneuver time. So we have real-time capabilities. And even though it's not, in some cases might not be real-time capable, we always have the fail-safe solution. So we don't really have to prove real-time capabilities for certification. And we have this intrinsic safety property that if you forget assumptions like certain traffic rules, the reachable set of other traffic participants would be overly large, which would just result in more cautious behavior, but never in an accident. However, accidents remain possible, but then we will not cause these accidents. An example would be that we are trapped in a traffic jam and somebody rear ends our vehicle. Then, of course, we have no way to avoid this, but then it's not our fault. Good. So now I'm at the end of my presentation, and then we should have enough time for discussions. I can also, in the meantime, bring up the Robco website in case you're interested. This is kind of the commercial version of these modular robots we developed in our lab. And the other one is Common Road, which is also kind of cool because we have a competition now coming up. So the group of John Dolan at CMU participated in some years where you can upload solutions. And as you see, we will have, this is not yet updated, but there will also be a competition for 2023 where you can compete against other teams worldwide for motion planning. Yeah.
Great. Thanks, Matthias, and thanks for this. Thanks for a great interesting talk. So it's always exciting to see how you combine, theoretical and practical things in a very good way.
Yeah.
So I think we'll have some questions more like in terms of Q&A, but maybe I can start things off with some maybe I don't know, more making it a little more interesting, the discussion. So I think this reachable sets in general are very exciting, but I think one of the questions that I've seen sometimes come up is that the original input is often probabilistic, right? Like you have some, I don't know, state estimate that has some uncertainty, or you have some estimate of your car that has some filter that has some uncertainty in it. And so when you try to use them, you essentially end up building this kind of threshold that's set at some risk level in some sense.
Yeah.
If you could comment on that a little bit.
Yeah. You can also use set-based observers instead of Kalman filters. So we have like this paper, for instance, as an example, a guaranteed state estimation. And there you compute the set of possible states. And they're also quite efficient nowadays. So if you look at the computation time for this was a 30 tank system, so it has more than 30 state variables. And these are the computation times in milliseconds. So some approaches like have require less than a millisecond. You can run it on 1 kilohertz, and that is an alternative. So we also want to do also more on new methods for sensor data fusion using set-based methods. But yeah, we haven't provided. So this is a rather new result, but for sensor data fusion, we don't have a provably correct method yet. And then of course you can say, yeah, but what about image recognition when you have a neural network? So I have one PhD student where we could verify like image computer vision problems for 50 by 50 pixel videos if you have some noise in the data, but not for like a high resolution camera. So then, yeah, there's still some issues to be solved. But yeah, we're trying to work our way up the pipeline up to the perception. But you're right. I mean, it's like in some cases you have only probabilistic information, and then you have to use, let's say, if you assume Gaussian noise, the 3 sigma confidence interval or so, and then you know, okay, from here on I have like assumption, so there's still a certain probability that something can go wrong, but after that there's everything is kind of safe, and you don't have to test at least the motion planner, but only maybe the perception system, which is also good, and maybe also not the Kalman filter, but you already know that if you use a set-based observer, then that also produces correct results. So
Okay.
it's a long answer, but yeah, it's we
I
try
think
to
yeah,
apply it for more and more problems.
so I think then maybe just a last, and then I'll there's lots of questions in the in the chat, but one more question maybe on the other vehicle prediction, right? I mean, there's basically your rules of the road, and then you have what people actually do, and then there is essentially social. And then it's what they could theoretically do, right? I mean, if you look at what they could theoretically do, you would never drive a car, essentially, right?
Yeah.
So you have to put some bounds there, in terms of, like, for example, in your results you show you don't ever see a vehicle crossing over into the lane when it comes at you, right? Like it's like capped at its own lane in some sense. And so, but if a vehicle behaves unexpected out of its norm, then you should probably increase that area, or if it does behave expected, right, you should have
exactly.
a smaller area.
Yeah, so we have the tool Spot, and this will be renamed Sonia, but we haven't released it yet. So it uses some assumption manager. So the thing is, first of all, every time we see that an assumption is not met anymore, we remove this assumption. So if somebody overspeeds, we remove the assumption that the vehicle doesn't overspeed. By the way, we always assume vehicles overspeed, but only to a certain percentage, like 20%. But if we assume that's not enough, we update this online. Then you could say, yeah, but if you don't update it fast enough, there can still be an accident. That's correct, but then it's not our fault because the other vehicle was grossly misbehaving, right? So the basic philosophy behind our approach is that we show that we cause no collision, and if a collision happens, it's not our fault, but if we can avoid the collision, we still try to do that. So that's one thing. The other thing is I have one PhD student who predicts when another traffic participant is about to violate a traffic rule using machine learning. Of course, this is not formal, but it, like, if you kind of feel like or see like, okay, this will most likely happen, then we already remove this assumption to have this extra safety. And yeah, and one more thing, we have now finally our own research vehicle. So we will test this now in the next years on the roads, and then I can give you more in the next. I mean, this kind of presentation I gave similarly previously, but the next presentation I can show you much more experiments. And we have a project with a truck manufacturer where we want to realize this in a real truck for highway driving, and there we will also have some additional data. But this is, of course, as you know, if you work on real system, it takes much more time to get all the systems working on the hardware. So that's I don't have any results on this yet. So the PhD students, 2 of them have started, but I can maybe show you results in 1 or 2 years.
Okay, cool, awesome.
Yeah.
So yeah, I'll hand it off to Nikhil, who's gonna kind of moderate the the session.
Awesome. Yeah, thank you so much. Thank you so much for the awesome talk, Professor Matthias. And I guess we can probably get started with the Q&A. So we have a question from Ali. Thanks for the great talk. What if we don't have safety specifications for the problem at hand? While we can assume that there are some good handcrafted specifications, can we always rely on having a neat set of safety specifications in the real world? What if those specifications are unknown constraints? So how would you approach this?
The thing is, like, if you have a safety critical systems, you have to spend a certain amount of time for good specifications. Of course, there are systems where this is not required. Like an app on your cell phone, you don't need that necessarily, because if something goes wrong, okay, your game just is killed, or what, like isn't working anymore. That's not an issue. But for safety critical systems, then often the certification agency already has certain a list of things that have to be fulfilled. Like if you want to certify a new airplane, or if you want to certify a train system or a nuclear power plant, then that usually exists already.
So I guess I can add on to that. Would like, do you have any insights as to what goes into the certification process? Like, how do regulators come up with these metrics, or like?
Yeah, the thing is, like, I talked with regulators. I don't talk with them frequently, but maybe once a year, to just see how the attitude shifts. The main problem is that the certification agencies don't have enough background in these new methods that I've shown you. So they are like hesitant to use this. So the best thing is if one of my former PhD students would work at the certification agency. But it's kind of getting better. So they are like saying they are interested in these methods. But I think if you want to really certify this, it will take several years. For instance, for this project with the truck manufacturer that I mentioned, after the project, they want to start this, but they also expect that this might take several years to get certified. Yeah.
Thank you. I think we have a question from Isaac. Would you like to, ask your question? Yeah, I don't think they're.
Maybe it's an audio issue. Maybe you can take another one and then come back.
Oh yeah, sure. Okay. I guess we have one question from Aris, I think.
Yes, can you hear me?
Yeah.
Yes.
Sure. First of all, thank you, Professor Matthias, for the talk. It was very cool. So my question is, for the last part where you were showing this idea of safety around like these manipulators, right? When if you're going to implement this into an industry, for example, would you have to have an additional like a perception device, such like an abstract, for example, to know to implement these like safe effects, or
Yes. So in the lab, you basically simply use a Vicon system.
Yeah.
But I mean, in theory, you can use it in the industry if you do the following. You have to have these markers, let's say on a vest, or also on your clothes. And if you see or detect that there is something, let's say through lasers or foot mats, and you don't see the markers, then the system would shut down. That's one option. Another option is use markerless systems, but then you need several sensors, right? You need
Exactly.
LiDAR, you need vision to
Yeah.
classify, and again, maybe these floor mats are quite good, because you can, of course, they don't detect you when you are jumping, but at some point in time you have to hit the ground again. And yeah, I mean, it's like you have to have several sensors.
Yeah,
It's,
yeah.
it's not cheap, of course, and you could argue, yeah, maybe it's cheaper to have a cage. But the thing is, like, once you have the setup, like the camera and the laser and so on, you can use it for many years. And every time you kind of change your factory, the cage has to be decommissioned, and you need a new one. And the other systems you can just always use, and you can also use it for, if you have several robots, they can use the same sensor setup, and you have much more space on the factory floor. So I think it's just a matter of time until this becomes commercially feasible. Right now, it's not there yet, and I hope that once Robco has more and more commercial success, that maybe they have deep enough pockets to also start this kind of certification process, which again, also for this application might take years. But once it's certified, it's really hard for competitors to achieve the same thing. Then it's kind of really cool. But it's yeah, it's like you need, I would say, at least, I think the certification process costs at least $10 million
Yeah.
at
Yeah,
least,
that's
and I think that's already on the lower estimate.
yeah. Very interesting. And then the other quick question was, so in those examples, right, where, for example, the vehicle stopped whenever like a person was in front of it, or the robot stopped whenever a person like had its hand there, right? Do you have like, does it have like a limit on how fast things appear? Like, for example, if something like gets around its fields of vision very fast, like, do you have like a type of like a limit on how fast you can perceive or detect these like intrusions? And
Yeah, so first of
with
all, I mean, the perception system has some delay. So we
yeah,
consider this delay in the verification. That's one thing. And the other thing is one verification cycle for this human robot coexistence scenario is less than 1 millisecond.
okay,
So in less than 1 millisecond, we know whether the action is safe or not. And actually, the reachable set computation. So we have, as I said, this is in the tool Sarah, and this is a ROS package. You can use this already, and there will be another ROS package for the whole approach, including the fail-safe trajectory generation.
I
But that
see.
we haven't released yet. But for computing reachable sets of humans, that is already a ROS package you can simply download and use. If you don't find it online, I can. But I think it's on my website. I have a bullet list of tools there. It should be listed.
Okay, yeah, thank you, Professor.
Yeah.
Yeah, I think we have a question from Divya. Could you tell us more about problems in visual estimation? Are there any direct methods, end-to-end neural networks, machine learning, factor graphs, to get probabilistic set-based reasoning for dynamic obstacles in the environment?
Yeah, as I said, I don't do stochastic methods anymore because it's more satisfying to prove something, at least from my personal point of view. But the thing is, like, is that we have this approach where we also verify neural networks. I mean, if you have, let's say, up to 100,000 nodes in your neural network, then we can still verify it formally. Beyond that, it's we're not yet able to do that, but we're making a lot of progress. And yeah, it's on our list, but we have like in the next Cora release, there will be also the possibility to verify neural networks. But the one thing that is also critical for neural network verification is that if the input set is very large, then sometimes we cannot verify things. But if you have some noise on the inputs, then we can prove correctness.
Yep. Thank you. I guess we have a question from Jay Patrikar.
Oh, I think maybe Isaac should go first.
Yeah, I think yeah, I can. Isaac can probably retry asking his question. I'm sorry, we can't hear you. Yeah, I think we could probably go back to Jay's question and we can.
Sure, yeah. Hey, thank you so much for the talk. That's pretty good. I was wondering, I know you discussed the idea of having rule specifications that are in the rules and include them to actually reduce the size of the reachable sets. I was wondering if there was also some discussion that we can have on including social rules into these things, rules that are not hard written down. For example, you're in a car. You don't want to, while it might be okay to cut somebody because the rule doesn't say that you can't cut them, but socially it's something that is just not good. You don't want a car to be just safe, but you also want to be writing algorithms that also nice on the road and not just safe. I was wondering if you have any thoughts on including these kind of rules into these safety-based reachable situations.
Yeah, I mean usually we just consider this as part of the cost or reward function, depending on whether we use optimization techniques for motion planning or for we use machine learning. So we just say it would be nice if. So we punish certain behavior, but we don't prove this because it's not in the traffic rules. Or do you mean that sometimes we on purpose don't respect certain traffic rules? So one more thing I can say is, like, I also haven't shown a slide on this, is I mean that comes not from us, but these are these rule books from what's his name again? He was at MIT, now he's at ETH Zurich. Emilio Frazzoli, right? So then where you say, okay, I cannot fulfill all rules, but I just maybe want to fulfill the most important rules. So these kind of considerations are also considered. And I didn't put it in my slides because I just wanted to give a brief overview of our methods. And yeah, so the soft things we just consider in the cost function, and in case we cannot fulfill all the constraints, we use these rule books to throw out less important things. So as an example, sometimes if you can avoid a collision, you maybe have to use a bike lane, which is usually not allowed to drive on. But if you can avoid a collision, then why not?
So in terms of removing those rules, so you basically remove a rule, try again, or like you have some kind of sequence of these rules, or how do you know which rules to remove?
Yes, they have priorities, and yeah, we remove the unimportant ones first until we and more and more unimportant ones are removed until we can have a solution which fulfills the important rules. I mean, this is this kind of concept from Emilio Frazzoli. It's called rule books.
Okay, cool.
Yeah.
So I think there's, I have one quick question. So in these scenarios you showed with like 4 vehicles on a highway, this kind of scenario, in some sense, if you would actually do this, the other agents' behavior would change based on your behavior, right? So I think you're just replaying the data here and then letting the other agents kind of go in between. Is that right?
Yes. So in the first 2 or 3 years of Common Road, that was the case, but now we have also interactive scenarios. Some of the videos you've seen are, let's say, recorded data, but we also have new videos where people react. And yeah,
Okay.
like in Common Road, you can, if you go to scenario selection, then you can wait a second. So no, wait. Prediction type. So then you have interactive, so where people react, set-based, and trajectory prediction. So trajectory means it's just pre-recorded, but there are also interactive scenarios now, which you can use. So there's actually the majority now is interactive, because that's initially we had to get things going, and then we just use pre-recorded scenarios.
Very cool.
And also we have a kind of, because whether you have autonomous ships or cars, it doesn't make a big difference. So we have now a common ocean, which is kind of the same thing, but just for ships. But there we don't have too many solutions yet, or too many benchmarks. But this is for vessels, for autonomous vessels.
we could probably contribute a common air one.
Yeah, we were thinking of that as well, but now we have common ocean and the common road, and yeah. If you have a lot of data for air, I mean, Josefina looks into this a little bit because we have a side project on inspection of power lines with quadrocopters, and that's of course safety critical because you shouldn't fly into a power line. There we are doing also a little bit of research in this direction.
Yeah, we have lots of data. So.
Yeah, I mean, if you want to share it, but yeah, I guess you want to maybe then have your own website. I mean, the thing is, what we are doing now is right now, Common Ocean and Common Road are separate websites, but we're building this Common X background so that all are kind of running on the same platform, but with just different content. And then we could, for air, we could easily use the same interfaces and just replace the scenarios and yeah, host such a website. That would be rather easy to do, but yeah.
Yeah, maybe we can have a.
So you can see that because we have now these 3 versions. I can also show you the Cobra version, but that is also not as well done yet as the Common Road. But this is kind of for these robots scenarios. It also looks similar. It's just as that is the same thing. And here you see the different tasks you can work on, and you also have a list of robots you can use for benchmarking. Yeah.
Cool.
Yeah. This is a 3D. This was a 3D scan, and yeah.
Yep. Thank you so much. I think this is all cool work, and I think we can probably stop the Q&A here. And yeah, thank you so much for doing this talk, Professor Matthias. It was
Okay. Yeah, thanks for having me. Good. Wish you a nice day. And yeah, I guess you're all a little bit hungry, or you ate during my talk. It's lunchtime, right?
Yeah. I mean, yeah.
In Pittsburgh. Yeah.
Yes.
Okay. Good.
Yep.
Thanks a lot.
Mhm.
Thanks. Thanks, Bastian.
Bye.
Thanks, Sebastian. Okay. Yeah. Bye.
Thank you.